Hi everybody, this is our video on how light hits gnomons on the Earth. And to make the point that I want to make, the first thing I'm going to show you is a really kind of a silly one, and that's what light would hit the Earth if the Earth was flat. And so I'm going to draw a little flat surface here, trying to show a flat Earth. And I know it's really ridiculous. Everybody knows that the Earth isn't flat. But we're going to go ahead and make a nice flat surface Earth here. And we're going to pretend that all the other truths of the Earth are still there. So in other words, the flat Earth still is on the orbital plane. And I'll go ahead and I'll make the orbital plane with a dashed line. And we'll say that light from the sun is still hitting the Earth the same way. So we'll say the sun is over that way. And we know that the light from the sun hits us in straight parallel lines, and that those lines are also parallel to the orbital plane because the orbital plane runs right through the sun. And so I'll go and rip my paper there a little bit. I'll make that for a beam of light, and I'm drawing these freehand as well as I can, trying to make these parallel. And I'll draw this as a beam of light. And there's a beam of light that runs right down the middle of the orbital plane, so I could draw that as well. So all in here, and there's of course an infinite number of these rays of light. Well, I'm going to go ahead and stick some gnomons on our flat Earth. And I'll stick a gnomon here, I'll stick a gnomon here, and I'll stick a gnomon here, and I'll stick a gnomon here. Now, the reason I did the flat Earth is to make the following point. And that is, if we have a flat Earth, it doesn't matter where we put the gnomon. Because since light would be hitting it in these straight parallel lines, every beam of light is going to hit the gnomon, so to speak, kind of straight on. Or if you're standing on this, it would look like the light was right above you. Remember when we held the light right above the toothpick? It didn't make a shadow, and that gnomon's not going to make a shadow if the light's hitting it head on. And light is going to do that to every one of these. It's going to hit every gnomon here absolutely head on. And every gnomon here is going to read the exact same altitude, which is going to be 90 degrees. And again, most of this, other than the flat Earth, sticks with what we know to be true. Orbital plane running through the middle of the body, straight parallel lines of light from the sun striking it, and in this case, 1, 2, 3, 4 different gnomons on our planet, and they are all basically going to read the exact same altitude of 90 degrees because we're flat. Now, we know that we don't really live on a flat surface. What we want to do is see how this changes once we move to the surface we do live on, which is, of course, a round surface. And just like before, I'm going to draw in some things we know. I'm going to go ahead and draw in the orbital plane on our picture, and I'll show that with our dashed line. This is going to be our orbital plane. And just like the picture before, we have straight parallel lines of light hitting us that basically are also parallel to the orbital plane. So there's a line of light. And of course, I'm not going to try and draw all of them because I couldn't if I wanted to. And there's a nice straight parallel line of light, and so on. But now, since the surface of the Earth is curved, all of a sudden, this bit about it doesn't matter where we put a gnomon, it will always be the same. It changes. Let's put a gnomon right here where the orbital plane is going through the Earth. That gnomon right there, now it looks so, we'll have that be it, is going to get hit by a straight line of light that's coming in like this. And that is going to be a 90-degree altitude. It's going to hit the gnomon straight on, just like all of these do. However, if we move the gnomon to a different part of the Earth, now that changes. So I'm going to go ahead and draw a gnomon right here. And the gnomon's sticking up. If you were on this part of the Earth, that would look straight up. Okay? And when this straight parallel line of light hits this, it is all of a sudden not hitting that gnomon straight on like this one is. This one actually is going to hit and make a shadow. And since we've got a triangle, we could measure that angle of the triangle and it would be not a 90-degree altitude because now it is throwing a shadow. So two different places, two different altitudes. And as we go up the Earth even further, we can see what else happens as a result of this. Again, the lines stay parallel to each other. I'm doing my best to try and draw kind of parallel lines there. But now this one has got a much different triangle than this one we just drew a moment ago. And there would be our shadow, and there would be our altitude. So you can see on the same time, because of this curvature, we get a gnomon that's not throwing any kind of a shadow, meaning the light's directly overhead at 90 degrees. We get this one throwing kind of a small shadow there, and I just would estimate that's probably about a 70-degree angle. And this one that's throwing a much longer shadow on the Earth, and I'm guessing that's about a 30-degree angle right there. So at the very same time, because of this curved Earth, if we move the gnomon on the Earth, we get a very, very different shadow. That same thing does not happen if we have a flat Earth where the parallel lines of light are striking every gnomon exactly the same. And this change of the shadow because of the curvature of the Earth is going to be extremely important in understanding what we're going to be talking about coming up on seasons and how the light hits us differently as we get different seasonal changes. So that's my movie on thinking about how light strikes a gnomon on a curved surface.